Welcome to today's webinar. Let's begin. I should introduce myself. I'm the Master of Ceremonies. My name is Nathan Bindoff. I'm a climate scientist and Professor of Physical Oceanography at the University of Tasmania's Institute for Marine and Antarctic Studies, and also part of the Australian Antarctic partnership program. Before we get into the presentation itself, let's acknowledge country, and as a reflection of the institution's recognition of the deep history and culture of this island, the University of Tasmania wishes to acknowledge the Muwina and the Palawa peoples, the traditional owners and custodians of the land upon which this campus was built, and pay respect to the elders past, present and emerging. It's a pleasure to be hosting this fourth Island of Ideas event. There's just a few housekeeping notes that we should talk about first. Some of you will be familiar with Zoom meetings, some of you won't be, but in this particular webinar, we have actually disabled the participants' microphones, the video, and the chat function and raised hand function. But that doesn't mean we don't want you to ask questions. It's really just so that we can make this webinar work. Questions are best and only done through the Q&A channel. If you look at the bottom of the screen, you should see a Q&A window. You can click on that Q&A and up will pop a window, and then you'll actually can type into that window. And at the end of the presentation by our two speakers from the Australian Antarctic Division, we'll be able to address those questions and then conclude. One thing that that's useful to know is that the event is being recorded, and as a consequence, it will actually be available on SoundCloud, just the sound, and both the images and the sound on YouTube, both of which can be accessed from the Island of Ideas webpage. It's my pleasure to introduce this very relevant topic, actually. The concept of heat waves, especially in the marine and Antarctica, is very new. And we have two speakers from the Australian Antarctic Division, Dr. Dana Bergstrom and Andrew Klekociuk. Dana is an applied Antarctic ecologist whose work evolves around Antarctic organisms and ecosystems work, identifying the risks to these ecosystems and the solutions to mitigate these risks. Dana has particularly focused on the impact of humans on the very large scale, for example, climate change, but also actually on a more micro scale, at the scale of a human footprint, which in Antarctica can actually cause significant damage. She's played major leadership roles in international Antarctic science programs. For example, the Scientific Committee on Antarctic Research's regional sensitivities to climate change. And in the same organisation, Evolution and Biodiversity in Antarctica program. And finally, actually, in the International Polar Year, there was an Aliens in Antarctica program. Her most recent research is focused on evidence-based conservation planning and understanding the rapid collapse of ecosystems in alpine areas on Macquarie Island. And our second speaker, who shares this part of the presentation, Andrew Klekociuk, is a principal research scientist in the Antarctic and Global System program of the Australian Antarctic Division, where he conducts atmospheric research. He also has affiliations with the University of Tasmania through the Australian Antarctic Program Partnership and also through the discipline of mathematics and physics. He also an affiliate of the School of Earth Sciences at the University of Melbourne and the School of Physical Sciences at the University of Adelaide. But Andrew is a graduate of the University of Tasmania, where he has both his Bachelor of Science with honours and a PhD in physics. So let me now hand over to our presenters. Dana, please take it away.
Thank you very much, Nathan. Good afternoon, everybody, and welcome to our presentation. We're one of multiple people on this piece of work, and we're now wanting to present that. Sorry about the technical details here. Can someone put that up on the screen for us? There we go. Okay, here we go. Okay, what we're trying to do today is going to bring you up to speed on a paper that we had published with our colleagues, which you can see here up on the screen, in Global Change Biology in March. And what we're talking about is a circumnavigation of a heat wave around Antarctica. Okay, we are having some technical difficulties. I need to get back to the last slide. Not working. Okay, here we are. So I'm going to talk about a number of places in Antarctica. I spent the summer at Davis Station, which is in East Antarctica, and the other significant station we have there is Casey, that I'm going to talk about. So Davis is in the Westervold Hills, and we tend to divide Antarctica between east and west, and that orange line you can see on the vision is that sort of rough division between East Antarctica and West Antarctica, where we find the Antarctic Peninsula. And right at the top of the Antarctic Peninsula, we have some islands, and here you can see King George Island, and there are some stations also on the actual continent itself, the peninsula, the tail of Antarctica, and there's Esperanza, which is the Argentinian station, and off to the side you can see Marambio, which is another Argentinian station, and a little spot in the middle called Eagle Island. So these are the locations that I'm going to talk about during this, my half of the presentation, before I pass over to Andrew, who's going to talk about the climate that we experience and the weather that we experience. I'm going to talk about what I saw down there, and also what my colleagues saw down there. So we're just having problems progressing to the next slide. David, can you try the new slide? Okay, so I flew down with colleagues to Casey Station, and then we flew across from the skiway to Davis Station, and this was in late November, arriving just at the beginning of December. Okay, so here are my colleagues. This is Paddy Virtue on the left-hand side, and Kath King, Paddy from the University of Tasmania, and Kath King from the Antarctic Division. And we have arrived at Davis on sea ice right outside the front of the station. And a sea ice in late November is 1.6 metres in depth. From here we can land planes, and we can use, as you can see, the Hagland in the back to get onto the land. From there, we've lost it. Sorry about the hiccups, everyone here. Okay, from there we went straight into field training, again late November, and you can see conditions there were, can we go back please? Okay, conditions there were, we're on a fjord. It's marine conditions, we have frozen sea ice, and we're able to walk across, and you can see stunning blue skies and lots of ice, and it's cold. Our goal for this season was to collect information on the plant distribution, so to create some baseline data to allow us to model where you find plants in the Westervold Hills. And you can see Patty here in the left with the hand lens looking at tiny plants. And this is what we find on the ice-free areas here, tiny plants from algae, cyanobacteria, lichens and mosses. And they're the biggest things you find in East Antarctica. And we were following on the footsteps of work done a long, long time ago in the 1970s and 80s. So here's a diagram from the 1970s of where you find mosses. And we went and visited a whole lot of these places as well. One of the sites we located, or we went back to, is a place called Mossel Lake. So there's a lot of freshwater lakes in the Westerwald Hills, these ice-free oases that we were there on, and there's over 300 lakes, over 4,000 water bodies. This particular lake, Mossel Lake, has been looked at for a long period of time, and it's quite famous for a very, very large moss bank. And on the left of the screen, you can see a photo from 1998. And all that green is lush moss banks. In January 2005, it wasn't looking too pretty. And here we can see a lot of white, which signifies dead mosses. And they've been covered in a lichen that I'm going to talk about. In January 2018, it was looking a little bit better, but still lots and lots of white. And the terms we use are moribund, which means mosses are sick, or dead, which everyone can understand. And in 2019, when we visited in December, not long after we had arrived, it looked very, very similar. Lots and lots of unhealthy mosses, lots of moribund mosses, and not much green. And as we progressed elsewhere, we were visiting places like this. This is Lichen Lake, as you imagine, with a name like Lichen Lake and Lichen Valley, a place very famous for its plants. We again were finding sick mosses. So here's a photo of one of these sites. And in fact, we went to over 72 sites. We went to 72 sites. We went over to 300 sites, but 72 of them had mosses. And we found that 84% of these sites had this epiphytic lichen with signals that the plants are sick or moribund. And in my notes, 64% of these sites, I actually expressed that there were lots of death and lots of moribund mosses. So what we're seeing here is that plants that were really, really healthy in the past that allowed you to get these really, really lush moss banks were not looking very good in December and early into January. We could find some healthy plants, which was good to me. As you can see here, this is what a lush moss looks like, but you can see Patty on the right is taking a photograph, and these mosses are growing in little tiny caverns, and that's about 1 metre from where her camera is. So if you're protected in the Westerwald Hills and you're a moss, you are looking green this summer. Next slide. Well, now I want to take you to the 22nd of January, and what was happening in Australia is that we were in the midst of this extraordinary bushfire period. The most extraordinary fires that were happening in Australia, covering an area which is tenfold more than what we'd usually have burnt in any summer. But in Davis, the view was slightly different. I want to introduce you to my accommodation first. TAD stands for Temporary Accommodation Donga in Davis Station, which is on the left. It's a series of containers. You can see my window and I've got it open. And this is a nice snowy day, but on the 22nd of January, this is what I was tweeting. It was very, very quiet. Usually that means it's snow. Pulled down the blind and I didn't see snow. What I saw was raindrops on my window. Now, rain does happen occasionally, and it's happening more frequently in Antarctica, but most precipitation is snow. So this was a really rare event indeed. So this is what it looked like looking out on the bay where Westerwald Hills Davis Station is, and the next image is what it looks like in November for a comparison. So it's typical that sea ice has broken out in late January, but what was not typical were these grey skies and rain compared to blue skies or snow. And it just happened that that day that it rained, we were heading out to Mossel Lake. We'll go to the next slide. And this, hopefully you can see this, this is the view through the helicopter window, and we were flying through significant rainfall. And the next image shows that when we got to Mossel Lake, we found the lake had flooded. Now, there had been a flood in the 1980s, but because we'd had quite a warm summer where temperatures were on average between 3 and 6 degrees above zero, there'd been a lot of snow melting in snowbanks, and also the local glaciers were melting as well. So coupled with the rain, these warm conditions had led to the lake to flood, and water had wicked through. And here's a quadrat, which is 50 centimetres by 50 centimetres. The left hand is in the December when I visited, and the right hand is now what we found in the 22nd of January. So water had wicked through. Some plants had drowned, but those areas that had got wicked water from the lake had actually recovered from that moribund state to a very, very green state. So here it was a quite surprise to go from grey to green. But if you can see on the tops of these little valleys, you can still see the white and grey bits. So there are still dead mosses here covered in this epiphytic lichen that I talked about, a thing called Caloplaca athelina. Next slide. Not only were we seeing areas that were getting moist recovery, it was a time where there was a significant change to what we normally see. There was substantial rivers flowing as water came down from the glaciers that surround the Westerwald Hills or from snowbanks. And pathways through the Westerwalds that people take to walk were inhibited because of these now raging rivers and just soggy areas that you couldn't pass, where usually you could pass over walking on ice. And we'll go to the next slide. And at this time, I also had an opportunity to fly to the Lasman Hills, which is another ice-free oasis near the Westerwald Hills. And flying over those glaciers, you can see significant melt on the surface of these glaciers. These little blue pools melted ice, reflecting the powder that's come up from the glaciers, from the rock under the glaciers. You could see streams, you could see rivers, and at one point we had a waterfall which came out mid-glacier into the local bay. Next slide, thanks. Okay, so that was what's happening in the Westerwald Hills. Elsewhere, we found that there's this heat circumnavigating around Antarctica. It began to the west of the Westerwald Hills and it was moving eastward. And at Casey Station, there was record Antarctic temperatures. We had a heat wave between the 23rd and the 26th of January, where minimum temperatures were above zero and maximum temperatures were above 7.5 degrees. And then there was the highest recorded ever, which was 9.2 degrees, which is about 7 degrees above the 30-year mean. This is our first record of a heat wave at Casey Station ever in all our records of measuring the weather there. And this heat moved around the continent and it reached the tail of Antarctica, the Antarctic Peninsula, in February. And there, as I showed earlier, Esperanza, the Argentinian station, had their highest record temperature recorded of 18.4 degrees on the 6th of February. This was the highest ever recorded in Antarctica. But 3 days later, Marambio recorded 20.7 degrees. And this is between 2 and 3 degrees above the record ever for Antarctica. So here we're having some extreme weather, well above what's been recorded before. Andrew will put this into the climate of Antarctica. So he will explain how we get temperatures of 20 degrees in the Antarctic Peninsula, and that's a lot. And a temperature of 9 degrees is significant for Casey Research Station. Okay, the next slide. Now, the impacts that we were seeing around the continent were either good or good and bad. So extreme temperatures and weather can be favourable to some ecosystems and not favourable in others. Here is a tweet from Lauren Wise, one of my colleagues who was at Casey, and she had gone out to one of the moss banks in Casey, and the melt that had come with the heat had again fed moss banks, and they were looking really, really healthy. So the moss banks in Casey and the ones at in the Westerwald Hills are really quite unique for continental or the eastern part of Antarctica. So here the warmth was quite good, but in other places, and here we have King George Island on the right-hand side, they were finding, our colleagues who have been part of this work were finding that the plants were in heat stress. You can see these mosses are different in colour. They have a pigment which is quite dark, and so they were absorbing a lot of heat. And so here, the heat wave was causing heat stress. We'll go to the next slide. And then other people were tweeting about what else was happening in the area. Here, Elisa Guerrero was recording with a thermal camera the temperature of gentoo penguin chicks. And the next image will show that she was picking up temperatures of the surface, the dark part of penguins, the black backs, were reaching temperatures of 50 degrees. Now that is quite a serious stress for a penguin that's used to Antarctic conditions. And of course they were smart animals, and the next image will show where they got to hang out. They of course went for the meltwater streams to try and cool themselves down from these conditions. Next slide, thanks. And weird things were starting to happen. At the Ukraine's research station, they're starting to see what looked like a massacre in Antarctica, but in fact it was red snow algae starting to bloom to form these bright red blood snow, as they were calling them. So we started to see ecosystems responding very, very quickly during this summer. And not only that, we started to see really dramatic changes. This is Eagle Island from NASA satellite imagery between the 4th and the 13th of February, where 20% of the ice and snow on this island melted. And so this has consequences for the ecosystems in the marine environment around, where you suddenly have a mass wash of fresh water into a marine ecosystem. So my last slide, I think, is the next one. What we see is wider implications. Extreme events are very, very short-term events, but they have longer-term impacts. They can be favourable in some areas if we have fresh water in plants. They could be detrimental if it's fresh water going into an ecosystem. And they also have more distant implications. And this came out the other day. Antarctic warm snap likely puts Australian wildlife off kilter. In Warrnambool's little penguin colonies, they found they were coming back later than they usually arrive. And there's also some ideas about food not being available for whales. And so Antarctica is what we think is, from the Antarctic Division, the centre of the planet, which has implications all around the globe. And so this extreme event is not only having impact in terms of time, it's also having impact in spatial extent. So even in Australia, there was people starting to pick up impacts from this extreme event. I'm now going to step out of screen, and Andrew is going to come on board. And he's going to explain the weather and the climate behind this heatwave.
Great, thanks Dana, and hello to everybody out there. I'm Andrew Klekociuk, and I'm going to tell you a little bit about some research we've been doing to look at the causes of these unusual temperatures. So first up, what really has caused these temperatures? And I'll give you a quick summary of what we've found. Basically, if we bring up the next point, we're looking at an interaction of various climate factors. There are large-scale drivers of climate across the Southern Ocean that are part of the natural pattern, but those natural drivers have been disrupted in this last summer by some unusual processes. And the next point, we're talking here about influences from the tropics, but also from the stratosphere, that region above the lower atmosphere from about 10 kilometres up, which played an interesting role, which I'll get to shortly. And then finally, this is all occurring on a backdrop of climate change, very long-term, decadal scale climate change, mainly from human influences. So now let's start to have a look at the factors here. So I've mentioned climate change, and in the Antarctic, various things are changing. We know that melting of the Antarctic ice sheet is contributing to global sea level rise. There are changes in the temperatures over Antarctica. West Antarctica and the Antarctic Peninsula are showing warming in various regions. The Antarctic Peninsula is actually showing the greatest warming. It's patchy in the West Antarctic region, and there's a little strong change in East Antarctica. And I'll come to why that's happening in a second. It relates to the stratosphere again. We also know that the Southern Ocean is increasing in its pH, and that's due to dissolved carbon dioxide. And there are also changes in the winds across the Southern Ocean, generally a contraction of the westerly wind belt over the Southern Ocean, which has been protecting Antarctica with some of the climate change. Now, some of that change in the wind patterns is actually coming from the effect of the ozone hole in the stratosphere, the ozone hole being a phenomenon we've seen since the 1980s, a cooling of the stratosphere and destruction of ozone above Antarctica in the springtime. It heals each year, but it has a lasting effect. And on top of that, we've got carbon dioxide changes, which are also cooling the atmosphere and creating conditions that are similar to the ozone effect on temperature I'll come to shortly. Anyway, the ozone layer being at about 20 kilometres altitude. Next slide. Okay, so I've talked about these sort of longer term changes. So the carbon dioxide and ozone changes occur over periods of years to decades. But a heat wave, as Dana's mentioned, is a relatively short term effect. So what can cause these short term changes? Now, a definition of a heat wave is a prolonged period of abnormally hot weather. In this case, prolonged is actually in terms of days, not months or years. And we see those around the world in various places. And of course, Dana mentioned that we've seen that in Australia this year. But what can cause heat waves, particularly in the Antarctic? It's cold there, we have to get heat in. And how do we do that? Well, we can transport it from lower latitudes, either by the atmosphere or by the ocean. We can have stationary weather systems. We see in Tasmania occasionally high pressure systems that park themselves over us. That's an example of a stationary weather system. And that allows the sun, in some cases, to beat down on the surface and heat it up. But we can have other forms of stationary weather systems, stationary lows, in fact, that can bring in bad weather. So there are a number of different processes there. Changes in surface properties. So I've got a couple of slides there that show the pack ice in the Antarctic. And the Antarctic ice sheet itself reflects energy back into space. But when we start to change the colour or the brightness of the surface, we can create conditions that allow heat to accumulate. So in those open water areas, for example, the ocean takes up heat, and that can have an effect on weather. The other part of the slide there shows the melt in King George VI ice sheet, which is one of those regions near the Antarctic Peninsula that also had melt. And you can see that NASA satellite image showing changes in the surface albedo, as we call it. Wind and snowfall can also cause heat waves by the wind driving heat in, and also picking up heat flux from the ocean. Snowfall, just the creation of snow releases latent heat into the atmosphere that can heat it up. And that's why sometimes in Hobart in the winter we actually get slightly warmer temperatures if it's raining substantially on the west coast. Anyway, so there are a number of different processes there, and they all were a factor in the heat wave that we saw this last summer. So what I'm going to be talking about a little bit here shortly are anomalies. So these are differences from the long-term climate, and we'll see some maps of temperature anomalies in particular coming up shortly. Okay, so moving heat around the planet, I mentioned the weather systems that can move or change the winds. Basically, the Earth's atmosphere likes to circulate generally from west to east. We've got the westerly winds, and that's particularly the case when you get higher up into the atmosphere. So this little diagram on the right really just shows what we call the jet streams that exist around the planet. Anybody that goes to Western Australia on the plane sometimes has to fly in the opposite direction to one of these jet streams, and their aircraft gets slowed down, but coming back home, you get into the jet stream and can come home quicker. These jet streams are caused by the temperature difference between the equator and the poles. That temperature difference drives a pressure difference, and the rotation of the Earth likes to whip the winds around from west to east and creates these streams. Anyway, one way of getting heat from the equator to the pole is actually if you can perturb one of these jet streams and push it further south. So that little diagram on the left below there shows a bit of the cutaway structure of the atmosphere and shows those jet streams. But importantly, the ones that I'm interested in here is the one called the polar jet, which is the one that forms near Antarctica, and the stratospheric jet, which is formed in the wintertime over Antarctica. And it's the interaction between these two that caused some of the interesting heat this last summer. Next slide. Okay, so it's going to get a little bit complicated here, and I hope I don't lose anybody, but I wanted to talk a little bit about one of the main drivers of this heat event this last summer, the Indian Ocean dipole, and that is one of the main factors that influenced Australian weather over the summer. The Indian Ocean dipole is a natural process in the ocean, and this last summer it was in what's called a positive phase. So we had cooler than normal ocean temperatures to the northwest of Australia, and warmer over off the coast of Africa. And that process essentially prevented a lot of rain from coming over Australia and allowed high pressure systems to form that transported heat across the country. So in the next little diagram here, I show the strength of this dipole over time. And in fact, this last summer, it's been one of the stronger episodes in recent decades. You can also see back around about 1998, a large positive event, but it's tending to trend towards more positive values. Now what that means, that's sort of part of the reason we're having less rainfall in Australia, but it's also a reason that the Antarctic atmosphere is getting more disturbed. On to the next slide. Okay, I'm going to talk about another factor here, the southern annular mode. May not be that familiar to people, but certainly the farmers take a lot of interest in this. This is a natural mode of variability in the Antarctic region, basically again relating to the westerly flow around Antarctica. Although it tends to be in a positive state, as it's shown here, where we get strong winds near the Antarctic coast, lower pressures over Antarctica, and slightly higher pressures towards Australia. And in that case, the weather in Australia tends to be a little bit drier, so this is one of the reasons the farmers are quite interested in this. Now, the southern annular mode has tended to be in a more positive state over the last few decades, and the next slide here will talk to that a little bit. In that positive state, as I mentioned, the winds are closer to the Antarctic and actually provides a barrier for getting heat into the Antarctic. So when the southern annular mode turns into a negative state, which it did last summer, it's actually weakening that barrier and allowing heat to get to the Antarctic. So the next little picture here just shows the trend in the southern annular mode over recent years. It's tended to be positive, but you can see right at the end there, it was actually below average this last summer. It's been lower before, but it's the combination now of this positive Indian Ocean dipole and a negative southern annular mode that basically weakens that halo around Antarctica, allowing heat to get in. To the next one. So the ozone hole. So another process that's important, I've mentioned before, the formation of the ozone hole, and that's been tending to push the southern annular mode into a more positive state. It's the cooling of the atmosphere above Antarctica when the ozone is destroyed that tends to be forcing the lower atmosphere. Now, this last spring, we saw a very unusually small ozone hole, a very weak one. And we looked at the size of the ozone hole. If I show the next picture there, this is the progression of the area of the ozone hole in spring over the last few decades. It's risen from the 1980s, and now that we're controlling ozone depleting substances, it's leveling off. But you can see this last spring, it was quite a small ozone hole in comparison to other years, and in fact similar to 2002 and 1988. And our colleagues that I work with, the next image here, we looked at temperatures over Antarctica at 60 degrees south. You can see the 60-degree south latitude there. It turns out that in the spring, we saw unusually warm temperatures. And that was one of the reasons for this weaker ozone hole. Warming atmosphere stops those reactions that destroy ozone. So, trying to put all this together next slide. So now we've got some slides here showing the warming of the Antarctic that Dana talked about, the progression of the warm areas. You can see in December, mainly over East Antarctica, moving around through Casey and then onto the Antarctic Peninsula. And of course, in there you can also see the very strong warming in Australia over the December period. And just noting those stations that we've mentioned. But basically this heat wave progressed around the continent due to the action of that, first of all, the Indian Ocean affecting the southern annular mode, and then the Indian Ocean effect also getting up into the stratosphere, weakening the ozone hole. And that's the final part of the story where the ozone hole effect reaches down into the lower atmosphere later on in the summer and causes that heating in the Antarctic Peninsula. On to the next one. So a little bit of detail here showing you some of the patterns over the oceans. Now I mentioned the negative southern annular mode, and in that case there we tend to have the westerly winds closer to Australia. That's certainly the case. This plot on the right hand side shows you the springtime anomaly in the wind strength. So the difference from what we'd expect from the long-term climate. Stronger westerly winds near Australia, so that's the sort of pushing up of the southern annular mode towards Australia, and a weaker belt near the coast of Antarctica, those blue colours. But by no means it was actually what we'd say a classical situation, more asymmetric. So not necessarily along constant lines of latitude as we normally see. So this is, we think, the Indian Ocean and part of the Pacific Ocean sort of distorting this normal pattern that we get. On to the next one. The reason we're interested in those ocean basins is that we can also see in the left-hand side there evidence of strong upwelling in the atmosphere, deep convection, so lots of cloud and storminess there, which is related to the sea surface temperatures that you can see on the right-hand side. The other thing you can actually see there is some very strong sea surface temperatures in the northern hemisphere, on the coast of the US and also off New Zealand. So some other patterns are actually involved here. It's not just the tropical forcing there, but there are some other factors happening as well. Next slide. And this slide shows you some evidence of the effects of those ocean basins. This is a plot of the wind on the left-hand side there in spring at about 10 kilometres height, showing you unusual patterns in the wind strength. In some regions, you can see those red regions, the wind is actually blowing from south to north, and in the blue regions from north to south. Small deviations from the climatology, but enough to highlight that there's a process there that's transferring energy from the tropics to the high latitudes. In the spring, that pattern there was sitting such that heat was being driven down into the Antarctic in those, generally the bluer regions. Those regions actually, the weather systems also reached down to the surface. And then later in the summer, we saw a movement of those patterns that tended to favour movement of heat into the Antarctic Peninsula region. The effect of the stratosphere was shown on that right-hand panel where you can see the warming in the stratosphere that affected the ozone hole coming down to the surface. So a combination of things, the steep convection in the Indian Ocean, distorting the southern annular mode, and then the energy from the waves that's been created in that region reaching up into the stratosphere and heating it. And then that also then coming down to affect the near surface. Finally, some lingering effects of all of this heat. So the main effects I've talked about, the temperatures near the coast, the warm air that's been driven into the Antarctic coastal regions by those processes, or aided by influence from the stratosphere. The sea ice, very important part of the whole climate system, very important for the ecosystem as well, providing a base for animals, but also important in the nutrient cycle. This just shows you a recent map of the sea ice in the Antarctic, and those red regions are regions of below average sea ice extent. So we think that part of the warming has influenced the sea ice extent around the coast, particularly from the Ross Sea right round to the Weddell Sea. And in those regions actually producing less sea ice than average. The plot on the right shows you the total Antarctic-wide sea ice anomaly in March. It has been trending upwards over recent years. I've highlighted the current value there, just a bit below average, but certainly if we look at the sector from the Ross Sea around, it is much below average than we're used to. So I've taken you on a whirlwind tour of the oceans and the atmosphere. I hope I haven't bamboozled you too much, but just going back to that statement about our prolonged abnormally hot weather, the definition of a heat wave. So our understanding here is that it's influenced by some fairly short-term processes, the changes in the Indian Ocean and the interaction with the southern annular mode. But there's some evidence that those processes are changing as well on a backdrop of climate change. And yet again, it sort of demonstrates that there's a lot of variability in the atmosphere, and it just really shows how interconnected the whole planet is. Thank you very much.
Thank you very much, Dana. Thank you very much, Andrew. And we do actually have some time for questions. There's one question in the Q&A channel, the question and answer channel. But I might just take the liberty, while someone else perhaps types in another question, of asking Dana a question first. In the evidence that you sort of gave for changes in the ecosystems, you pointed to positive changes and you pointed to negative changes. On balance, were there more positive or more negative in that evidence?
We don't really have a strong picture either way at the moment, Nathan. It depends again on where you get free water, which is liquid water. So the moss banks that we saw, once there was some wicking, that was positive, but certainly areas were going under more heat stress. So these events have long lag times. There was an extreme event in 2001 that was right across the entire southern hemisphere, and in Antarctica and the Ross Sea areas they had flooding there, and they showed that there was a detectable change lasting almost a decade long. So these things we'll start to understand over the next 10 years.
Thank you. So let's go to some of the questions in the Q&A channel. I want to hold off on the very first question and go to the second question. The second question is, I wonder if understanding the southern annular mode and other processes has predictive power for the 10 to 20 year horizon. So maybe that's Andrew.
Thanks. Yeah, that's a very interesting question and a very important one, because we do want to be able to foresee the future with greater accuracy. From our climate modelling, we definitely see trends in the southern annular mode, and we know the drivers of those are related to ozone in the summertime, but there's also a backdrop of longer term changes in the southern annular mode related to the greenhouse gas, particularly the carbon dioxide cooling. So yes, that's a very important one to get the trends right. Also getting the interannual variability is very important. Our models still can't quite capture some of that variability. It's the sort of an example here of the interaction between the oceans and the atmosphere and the timescales of those. But certainly it's a major effort to improve decadal prediction, is to get that southern annular mode predictability right. It has some persistence. We know that while the southern annular mode does vary from month to month, there's some memory of past months in there, and that does help us to give some predictability.
Thank you. So actually the questions are building up very nicely in the Q&A channel. I'll just go to the next question because I think it's for you, Andrew. So Andrew, you've shown that the March sea ice happened earlier in the season, like January, for example. I think this is, I'd also liked your zonal plot. I was waiting for a 3D picture. So what does the 3D picture look like?
Yeah, so in terms of the atmosphere, a lot of those, I showed you some different levels near the surface and higher up, but the plot of the winds, the meridional wind anomalies, they map down to the surface. So you can kind of imagine cells of change. It's on a backdrop of all these weather systems moving through, but there's some long-term influences that subtly change things. So you can kind of start to build a picture by looking at some of these plots. So I hope I've answered that one, but yeah, some of those different levels allow you to do that.
Thank you for that. I'll just simply move to the next question, and this one's on a much longer time scale. The question is, how is the current interglacial cycle we are in influencing the weather patterns we are seeing?
Yeah, it's an interesting aspect. Certainly the interglacial periods, there's a backdrop in the climate signal that we are actually seeing. I guess we've perturbed the oceans and the atmosphere away from that backdrop, certainly by warming near the surface and the heat uptake by the oceans. So there's still some memory of those interglacial drivers there, the planetary periods, the Milankovitch cycles, but that's happening on this new, more rapid change. And so the whole Earth system is really trying to equilibrate to this new forcing that's taking up. And I think that's certainly a much stronger influence at the moment.
And I'll move to the next question. Actually, there's a lovely list of questions here. This next one is actually about the ozone hole and its influence on the weather. So here it is. Does the warmer weather over Antarctica make the ozone hole bigger, smaller, weaker, stronger? And what does weaker mean? So this is really just teasing out changes in the ozone hole and its influence.
Yeah, okay. So the destruction processes around ozone are temperature dependent. The colder it is, the more ozone is destroyed. It's a multi-stage process, but basically it relies on the formation of small icy clouds in the stratosphere. that chemically alter the atmosphere. So the colder the stratosphere gets, and it's getting colder also because of increasing carbon dioxide in the atmosphere. We're familiar with the warming below, but when you increase carbon dioxide at low pressures, you actually cause a cooling of the upper part of the atmosphere. So when the atmosphere is colder in the spring, more chemical processing happens, and it's really when sunlight falls on that, the atmosphere that ozone gets destroyed. So in summary, colder is worse for ozone destruction, but as we start to have stronger effect on the ozone depleting substances, that effect will start to diminish, and we're actually going to be seeing over the next decades much stronger evidence of recovery in ozone, and that will start to warm up the stratosphere slightly. We'll actually have more ozone, which will be good for returning that equilibrium. So ozone destruction, temperature dependent, but then it's that cooling of the atmosphere from that ozone that eventually makes its way down to the surface and alters the wind pattern. So I hope I've covered a few things there. Warmer it is, the less ozone is destroyed, and that looks good at the moment. If you remember back to that plot I showed, we had a small ozone hole, but that's abnormally small compared to what we'd expect based on the amount of ozone depleting substances still there.
Okay, so it was a real anomaly. So let's just move on to the next question, and this one is really about the comment Dana made about the impacts on the little penguin in Warrnambool. Here is the question. There was mention of the observed impacts on Australian penguins from the heat wave and general warming trends of 2020 in Antarctica. And then what are the predicted longer-term flow-on impacts for Australian weather patterns from Antarctic landmass changes? Maybe that's a question for both of you. Have a go.
I think I'll hand over to Andrew for that.
Yeah,
it's more of a climate thing.
I can address that second aspect. So Antarctica has an important influence on southern Australian climate. So generally as Antarctica warms, we'll start to see more variability in climate. The Antarctic has a moderating effect generally on the climate of the southern hemisphere. As that whole area starts to warm, we'll see potentially additional changes in our latitudes. In terms of the penguin influences though.
The issue also is the overturning circulation. So when we have water coming in winter to create what's called the overturning circulation, where you have what's called Antarctic bottom water and driving nutrients up, that requires having saline conditions to drop into the lower part of the ocean and push the water up. So as we start to slow that down by having more fresh water coming into the system, we're going to find that the overturning circulation won't be as strong. And so we will start to get mismatch between when nutrient is meant to appear to be a source of food versus the higher predators relying on phytoplankton. So these things we can expect is going to be disruption. And the signal about the little penguin was again about a mismatch of when nutrients turned up, when breeding is happening. So these are some of the things that will start to be tangled up with warming of Antarctica in the future. But how they are will require a lot more focus on modelling and understanding how things are interconnected. So having sort of long-term understanding of the connectivity in our ecosystems is going to help us sort of untangle these sort of network of connections.
Thank you, Dana. So the next question is around ice cores, but really it's a question about how extreme the last year was. So the question is, could the ice cores that are being brought up show whether these patterns have occurred over the millennia or in the past? Or how extreme was the heat wave in our experience?
Yes, so one of the limitations in ice cores is getting very, very high resolution to the scale of days or weeks. And generally we have seasonal records or annual records. In the more recent times, we have sub-seasonal, but generally in the longer term, it's annual or even decadal. So we have to be talking about extremes on those sorts of scales rather than the more shorter term ones that we've been talking about here. But that's certainly a very active area of research, is to look at the variability of the whole climate system using ice cores as a proxy for those. And we measure temperature through proxies of the trace gases in the ice cores. So it depends a bit on the time scales that we're talking about, but certainly we can see in the ice core record that the current warming, the rate of warming, is unprecedented in a long-term record.
And in the sense of the instrumental record, Andrew, how unusual was last year's heatwave? Yeah,
so one of those plots there I showed some hatching on the diagram. You can go back and have a look, where the single hatching indicated the event was sort of roughly at the 15% occurrence level over the last 40 years. We do see other heat waves in the past, and Dana talked a bit about one of those a minute ago, 2001-2, which incidentally was sort of a different setup of the atmosphere and ocean, and strongly influenced by actually a marine heat wave in that case. But in the instrumental record, well, we really only have good records, surface measurements since the 1950s. There are spot measurements before that, satellite measurements since '79. So this particular heat wave, at least at Casey, in the 30-year record that we have from the current Casey station, is unprecedented. It's a rare event in Antarctica, but the extremes that we're seeing are quite rare locally.
Okay. And now we're going to move back to ecosystems. This is a question for Dana. Dana, you've shown evidence in the field. Have you been studying these plants in the laboratory or nursery environment to develop a richer understanding of how these plants work and respond?
Yes, we have with my colleagues. The lead author on this work is Professor Sharon Robinson from the University of Wollongong, and she and Professor Marilyn Ball at ANU, the three of us have been working on how these plants function. And so we have an idea about what is critical to how they thrive and grow. One of them is that we're starting to look at isotopes, which is giving a signal about how long ago water was available in what year. Like an ice core, a moss core can do a similar thing, but only over a short period of time, as in 200 years. So we're starting to do this right now. We're going back in time to see what's happened to the life of a moss single shoot. And so we're getting some ideas like that. But one of the things we do know is that critical move between frozen to having liquid water is so important with regard to the life of mosses. So in the past, we've had an event where it actually rained at Casey Station in the middle of winter. And no one was there to see what happened. But when Sharon turned up the next season, a lot of the plants weren't very well. And so we set up what we call Casey North, which was at ANU in Canberra, and we did some experiments where we put plants into their Antarctic conditions, and we found that we could take plants down to -20 and then bring them up again, and they were very, very healthy. But if we rained and I put some liquid water on them, we found the plants weren't responding very, very well because they started to freeze inside their cells. So we have some really good ideas about how these plants function, and it's the areas a lot of us are continuing our research.
Thank you. Here's a very open-ended question. It was the very first question that got asked, but in the introduction, Dana, one of your specialties was mitigating some of the problems. So what can we do on an everyday human level to help? It's very open-ended.
Okay, so the first thing here is to understand that underpinning all of this is climate change. And so the things that we can do on a day-to-day basis is to try and reduce the amount of carbon going into the environment. So no questions about it. Our entire planet, the entire communities across the planet has to reduce our carbon. And so that will start to take off the climate pressures in these ecosystems and in our ecosystems that we live in, such as Australia and the bushfires over the summer. So that's the first thing, is a global response to climate change and reducing carbon. At a local level, what we want to do is reduce pressures. So in Antarctica, we can look at the things that are going to cause stress in these environments. So if it's lack of water, we might want to set up snowbanks which allow them to, snow to melt to feed these moss banks. So we can start thinking about actions that can help the things that we value to survive. And so we can work at a global level, but we can also look at a regional and a local level. The first thing is to understand things that we consider to be valuable, be aware that climate change and these extreme events are going to happen more often, so anticipate things, and then work out actions to reduce the pressures that we're seeing.
Thank you, Dana. I think we'll just come to our last question. We've had some very nice comments. Here is a comment. This session would make a great Radio National Science Show special. Someone should contact Robin Williams. Take that as a compliment. And just let's have the last question here, which is one about long-term studies on cloud cover in Antarctica. Have there been any long-term studies on cloud cover in Antarctica? And if so, are there any correlations with temperature change? And is there evidence of increased surface solar irradiance in the Antarctic region? And that would be the last question. Take it away, Andrew.
Okay, it's an interesting question that relates very much to the Australian Antarctic Program Partnership, where we're actually trying to understand the microphysics of clouds and trying to understand the long-term changes. Cloud measurements actually are quite difficult to do. Observers in the Antarctic have been looking at them for a long period, but actually quantifying them is quite difficult. Satellites have a problem in looking at clouds over the Antarctic because their surface is so white, it just looks like a cloud. But there have been studies of the cloudiness, and there is a relationship with the southern annular mode. So as the westerly winds strengthen, as the SAM goes into a more positive state, pushing the cloud over the Southern Ocean a little bit further south. And so there are some long-term changes there. And that also affects the radiative balance. The questioner is quite right referring to that. So basically, clouds are very important in that energy cycle where the sun's energy has to get to the surface in some form. It can get there directly, or it can get there indirectly by re-radiating from clouds. So yes, there are long-term changes. Our program's working on improving models to represent clouds better and to look at the long-term implications. One of the other impacts is that as the SAM, the westerly wind belt, contracts towards the Antarctic, actually the easterly winds around Antarctica are actually weakening slightly. And that's also affecting the cloud properties, the cloud occurrence over the sea ice zone around Antarctica, and there are some actually changes in the reduction of cloudiness in some regions. In terms of the UV measurements, there's certainly long-term measurements of UV at our stations, and we're seeing a change in relation to certainly the ozone hole. That's the shortwave part of the UV. The slightly longer part of the shortwave spectrum, more into the visible. It's only recent, in the last probably 10 years or so, that we've actually had very high precision measurements. Making sure that we calibrate those is quite important. There are very subtle changes happening in the radiation balance, and that also relates to cloudiness and the albedo of the surface, the sea ice concentration, also the properties of the surface.
Thank you very much, Andrew. Thank you both Dana and Andrew for their wonderful talk, and thank you for the participants and the great questions that we've had. And some of you may have noticed that there are some more events coming. Good afternoon.